Welcome back to ECE 340. Homework number 4 is that due? I can't even keep track of the days. That's not the right date, is it? I don't remember when it's due. I think it's a week from today that I decided to have it due. So the 28th is when homework number 4 is due. Homework 5 will be due basically the lecture period before our exam. Well, that's how close we are to the next exam. It's rolling around quite quickly. What I want to talk about today is solutions or solving these state space equations, and we'll start with a very basic example, something that we hopefully all feel comfortable with. That's what we want to do if we're looking at something new, is to go back to something that's familiar. We'll look at the solution of that first order example in the time domain and in the frequency domain, and we'll go back and forth. We'll examine what we might need to do if we're going to sketch that waveform or that result in MATLAB. How do we create that, or what do we need to pick? And again, it's those two questions. How long do you simulate, and how fine do you chop up the time axis to make that simulation happen? We'll then talk about approximating the solution, and that will lead us into hopefully seeing how that makes the connection with an nth order, meaning if you now understand the first order, the process is the same. It's just you have to preserve matrix multiplication. If you now had a 10th order system, you could do it mechanically the same way that we've just done the first order system. That's the idea. If we get that far, we'll start talking about Bode plots. And so that gives you a feel for where we're headed, or what you need to be looking at reading-wise in the textbook. Let's start by solving a familiar problem via the state space formulation. If you had to guess what I'm referring to when I say our familiar example, now you might be thinking when you were growing up and you had something that was very comforting to you, maybe a pacifier, maybe a blanket, maybe a stuffed animal. Now what do we go back to? It's the low-pass filter. That's now our comfort mechanism. Here's our familiar example. We have a source. And this series RC circuit, where the output now is taken across the capacitor, or that's the capacitor's voltage. If we're wanting to solve this circuit or find the state space representation for this system, what's one of our first things that we need to do? Now we need to find our state variables, don't we? If we're going to do this in the time domain, we're now looking for an x prime equation. It's first order. We should just be getting one of those. What's the state variable that we'll pick for this system? This is just the voltage across the capacitor. So that state variable, Q sub 1, if we really even need to subscript it since there's only one, that's the same as the output Y. Let's now create the governing dynamics, or the model of that system, and it might be just as clean to write a KVL equation for that system. And if we do, starting at the lower left, we go through the source in the opposite direction. Then we have plus R times I of t based on the I that we've defined. That's the voltage dropped across the resistor, and then we have the voltage dropped across the capacitor which is simply what we defined one of our state variables, or the state variable, to be, which was q sub 1. This is a true equation that governs the relationships between the inputs, the state variables, but unfortunately it has a new variable in there that we really need to get rid of. The I, that's extra. We only want one state variable, so we need to find this state variable in terms of itself, the input, and its derivative. And we can do that in what way? What do we need to remember? We need to remember yesterday, don't we? Where we were having something coming out of the sky. Maybe it wasn't always ice, but occasionally at the start I think it was sort of ice-like. It turned into snow, but now this ice is for our capacitor, which says that the capacitor current, which in this case, since it's a series circuit, is just the I that we defined, is equal to C, and then the capacitor voltage, which is q sub 1, its derivative. We can now use this I to replace the I in our true representation of the system dynamics and end up with the state-space relationship or differential equation that we need. We have minus x of t plus r times c q1 prime of t plus q1 of t is equal to 0. That's not in the standard looking form. We can create that standard form by isolating q1 prime on the left-hand side, dividing everything by RC and putting everything else on the right, and we have minus 1 over RC q1 of t plus 1 over RC x of t. And that is a state-space representation of our low-pass filter, our first-order circuit. What's the A matrix? Maybe you don't think of scalars as matrices, but in fact this is what we were calling a matrix A. That's a 1-by-1 matrix. It's a scalar, but it's a 1-by-1 matrix, where in this case A, which I think subsequently, to emphasize the fact that it's a scalar, I'll just say is little a, is this minus 1 over RC. If that's A, then our input matrix B is right there. It too is 1-by-1. And to emphasize the fact that it's a scalar, let me just call that little b for now. And that is 1 over RC. If somebody wants the output equation, that's pretty easy. Y was just Q1, but if we write it in state space form, this is now our C matrix. That's also 1-by-1. Here is our D matrix. We have one output and we had one input. It's 1-by-1, and we have then C is just 1. Questions on that? We've now derived this familiar system expression in a state space formulation. We have the A, the B, the C, and the D. Question? And now what we have not yet done is we have not worried about initial conditions. This doesn't worry about initial conditions in terms of writing the relationships, but if we want to solve it, we need to account for the initial conditions. Let's go ahead and simplify this maybe a little bit by selecting some values, and you know which ones I'm going to pick. Let's just make them 1. And now we end up with our equations being q prime of t is equal to the A matrix, which is just minus 1 over RC, becoming minus 1, plus the B matrix times the input. And Y is simply C, Q, and in this case, C is this 1 by 1 matrix that's 1. What we want to do is solve this. This is a first order differential equation, and if we can find Q of t, then we have the output Y. Yes? So I'm trying to simplify things. I picked R and C both to be 1, so those basically get thrown, or they get absorbed into this notation. We want to find a solution. If we can simply find the solution for Q of t, which is the solution to a first order linear differential equation. Does everybody remember their differential equations? And we haven't yet specified what the input is, x. We like to derive this really in general. Well, maybe we don't remember our differential equations, homogeneous, particular, different ways of solving differential equations and specify or making that particular to a linear set of equations. Let's go somewhere where we are comfortable. This is the time domain. What if we take that into the frequency domain? Let's now go into the frequency domain. And now we need to Laplace transform a derivative. What happens when we Laplace transform Q prime? So we're Laplace transforming this equation and we want to now do that because we think, well, this will maybe make our life a little easier if we want to solve this because we don't want to go back and remember our differential equations. Let's just go into the frequency domain and do some algebra and then figure out what's going on. What's the Laplace transform of a derivative? So we have to multiply the waveform, the function whose Laplace transform we're finding, and we're calling that, let's say, capital Q of S. Again, this is just a scalar, but we multiply it by the complex frequency variable S. Do we need to do anything else when we Laplace transform a derivative? We do have to now account for the initial conditions. We now have minus Q of 0 minus, and that's the value of the state Q, or that capacitor voltage at time t equals 0 minus. Now if we went back to what we had before, we now have this piece was just little a, this piece was little b, and if we needed it, I guess that was little c. Now if we Laplace transform the right-hand side, we have a times capital Q of S plus b times capital X of S. Let's collect our terms that are common, and that then involves a couple of terms with capital Q of S. We bring the a over to the left, and let's push that initial condition over to the right. That then gives us a positive Q of 0 plus b capital X of S. To emphasize that eventually we will be doing this for matrices, let me just say, oh, this is now, let's invert Si minus A on both sides, or multiply both sides by Si minus, or S minus A inverse. And now what do we have? Well, in fact, we have this Si minus A inverse is just a scalar. So let's go back to the easy thing, or the cleaner version of this. Since it's a scalar, we can just plop that down in the denominator. And we have the same thing for this second term on the right-hand side. We have plus b over s minus a times capital X of s. What I want to do now is actually pull this back into the time domain. Now that I have, really, capital Q of s is the solution of the state variable in the frequency domain. To get little q of t, will just require that we inverse Laplace transform what's on the right. And that's made up of two pieces. This piece is straightforward, I hope, to inverse Laplace transform. If we do, what's the inverse Laplace transform of that very first term on the right? We have 1 over s minus a that we need to inverse Laplace transform. Q is just a constant, isn't it? That's our initial capacitor voltage. That's the initial condition. This now is e to the at times that initial condition. Now what we need to realize is this is a little bit more interesting or involved. This is now a product of two terms that are functions of s. And what do we remember happens if we multiply in the frequency domain? What happens correspondingly in the time domain? That's a convolution, isn't it, between the resulting waveforms. But we already know what this looks like in the time domain. You just told me that that has this e to the at behavior. That's now the time domain waveform, and this one's time domain is just some generic x of t. We now need to convolve this e to the at with x of t. And we know what the convolution integral is. This now becomes this, so this multiplication in the time domain is going to give rise to convolution, this multiplication in the frequency domain gives rise to convolution in the time domain. And convolution integral says we have this integral from 0, we're starting at time 0, up to the present time t. We now need to have something that's flipped and slid, and let's flip and slide the e to the a piece. We now have e to the a t minus lambda b x of lambda d lambda. That now structurally is going to be the same kind of structure that we will see when we go into the matrix solution of this state space formulation. In this case, we can see that the right-hand side, or the state variable, is made up of two pieces. A piece that's a result of the initial condition. If we had 0 initial conditions, this would go away. And we have a piece that's a function of the forcing function. So here's our forced response. We have an initial condition response. And we have a forced response. And again, in this formulation, we are, in this example, we had A is equal to -1, and B was just equal to 1. If we wanted our output, which was the voltage across that capacitor, we would have it by simply setting that equal to whatever we just found for Q of t. This is now our result, or the output equation. On your homework, you're going to have to be doing some solutions, in particular maybe for using the Laplace transform technique to find solutions to differential equations. And we can do that for this case. There's really the solution in terms of a time domain expression. Given x, you can now find via the convolution and the incorporation of the initial condition whatever Q of t is going to be. Let's now look at this for some particular values. Suppose that the initial capacitor voltage is 2 volts. And now let's say that somebody actually tells you what the forcing function is going to be, x of t. Suppose they say that's e to the minus 3t cosine of 4t u of t. And what we want to do is now find Q of t. And you're going, I don't want to convolve this x of t with another exponential. That might be integration by parts. So let's go back into the frequency domain to do this. So you're going to maybe do this on the homework, so let's just remind ourselves what's going on. We can now go back to the expression for capital Q of S. We have A, that was -1. This now becomes S plus 1. Q of 0 minus is 2. So we have 2 over S plus 1. Well, that's easy to actually find that piece of the solution for little q of t. This becomes 1 over S minus a minus 1, or 1 over S plus 1, times capital X of S. We need to Laplace transform little x of t. What is capital X of S? Do you remember your Laplace transform of damped exponentials, or exponentially damped sines and cosines? The damping gives us this shift in frequency. If we just had the cosine, if we didn't have this exponential damping and we just had cosine of 4t, we would be having s over s squared plus 4 squared, wouldn't we? But since we have this exponential damping, we need to replace s with s plus 3. We have s over s squared plus 4 squared. We now replace the s with s plus 3, and we end up with s plus 3 over s plus 3 squared plus the damping, or the damped oscillation, which is 4, and we square that. Now we have capital X of S. We can find the expression for Q of S based on everything that we've been told. The first piece is 2 over S plus 1, and the next piece is 1 over S plus 1 times S plus 3 over S plus 3 squared plus 4 squared. And you did this on exam 1. If I ask you what's the structure of little q of t, you should be able to tell me what the structure of little q of t looks like based on this expression. Now what we may do is we may just go ahead and do this in two steps. We may say capital Q of S is equal to capital Q sub 1. That's going to be easy, plus maybe a capital Q sub 2. And just play with capital Q sub 2. Since I'm assuming we can pretty quickly inverse Laplace transform capital Q sub 1 of S. The Laplace transform is a linear operation, and so that allows us to do this. Meaning, little q of t, what is little q sub 1 of t? That's 2e to the minus t, right? Now, what's the structure for q sub 2? Little q sub 2 of t. Or what's the partial fraction expansion of capital Q sub 2 of S? How many pieces do we have? Generically, we have 3 pieces. We have 3 poles, don't we? 2 of those poles are complex. So depending on how you want to do this, if you want to do the complex algebra, then you might keep those as complex roots. If you want to keep everything real in terms of real coefficients, let's just then collect 2 denominators that look the same. One will be a cosine and one will be a sine that's exponentially damped at the same amount. And we have another term associated with this pole at minus 1. And where are the poles due to this forcing function? If you had to sketch those in the complex S-plane, can you sketch those? Based on this factored structure, that should just be coming at you in big, bright letters. Where is it? Minus 3 plus and minus J4. That should be fairly quick to find. These poles are at minus 3 plus and minus J4, which now says that we could write this as some structure, alpha over S plus 1, plus, let's say, the cosine piece, and the sine piece. And there we have the coefficient times the omega sub d, the oscillatory damping. Let's now find alpha, beta, and gamma, just for grins. You'll need to do this on your homework. And now we have this is really equal to q sub 2 of S, which is this expression that we had before, S plus 3 over S plus 1, S plus 3 squared plus 4 squared. Is it clear what I'm going to do? I'm going to, for now, neglect this 2e to the minus t and simply say this partial fraction expansion is equal to capital Q sub 2 of S. This will now be my left-hand side, and my right-hand side will be the alpha, the beta, and the gamma term. And I need to find alpha. To find alpha, I simply multiply everything by S plus 1 and then let S equal to minus 1, or set that factor to 0. And that will then isolate the alpha. Alpha then is going to be S plus 3. I've just canceled the S plus 1 factor in the denominator of that left-hand side, and I now have S plus 3 squared plus 4 squared. And I'll evaluate that at minus 1. Now I know what alpha is. Alpha is 1/10, and that's the coefficient associated with another e to the minus t decay. Questions on where that came from or how we found that? What if we want to find beta? We can do it many, many, many different ways. We could put all of this red piece over the same common denominator as the denominator for q sub 2 of s, and then we'll get some numerator that has all these terms involving alphas, betas, and gammas. We could equate coefficients, and we'll get 3 equations in 3 unknowns, and we could solve that simultaneously. I don't want to do a 3 by 3 matrix inverse to find alpha, beta, and gamma. So let's see if we can find beta by itself another way. Here's one approach that I kind of like, and I don't know if you've seen it before. Let's see. We want to find beta. What I'm going to do is every term, or the left-hand side and the right-hand side, I'm going to multiply both sides by s, the complex frequency variable. And then, after I've multiplied both sides by s, I'm going to let s go to infinity. Because that partial fraction expansion is true or valid for all values of s, for all frequencies. Let me multiply by s, and then let this s march off to infinity. Let me see if I can do that. So on the left-hand side, what I'm really doing is I'm taking the limit as s goes to infinity of s times that left-hand side. That's my left-hand side. That's s times capital Q sub 2 of s. And I want to look at what this does as s goes off to infinity. As s goes off to infinity, what am I really wanting to focus my attention on? Probably the coefficients of the highest power of s. That's going to dominate, isn't it? In the numerator, what's my highest power of s? S squared. And then I have plus 3s. But as s marches off to infinity, s squared is definitely going to dominate 3s. What about my denominator? What's the highest power of s? S cubed. Now I have s squared, effectively, over s cubed, effectively, as s marches off to infinity. That's now 1 over s. Right, I can cancel the s squared out of both terms, effectively, because they're going to go to the infinity at the same, and they'll give us 1. And now I have 1 over s. Does everybody see what I'm trying to do? Now I have the limit of 1 over s as s goes to infinity. What's that value? That's 0. So my left-hand side now is simplified down to just 0 by multiplying by s and letting s go to infinity. That was the left-hand side, s times q sub 2 of s. Now that's going to equal each of these 3 terms multiplied by s and letting s go off to infinity. If I multiply this first one, alpha over s plus 1 by s, and let s go to infinity, what falls out? I have alpha s over s. Those s's go off at the same rate. I'm just left with alpha. Does everybody see that? This now, the first term on the right becomes alpha. What about the second term? That's the beta piece. I multiply it in the numerator by s, and I have an s squared up top. I have an s squared downstairs. What does that become as s marches off to infinity? Beta. Now, what's the gamma piece look like? I've multiplied it in the top by s. I have s squared downstairs, and I'm letting s march off to infinity. That one goes to 0. Now I have 0 equaling alpha plus beta. And I just found alpha before. This now tells me or gives me a way to pretty quickly find beta. Beta is just minus alpha, which I found earlier to be this minus, or alpha was 1/10, so beta becomes minus 1/10. Now I have two of the three partial fraction expansion coefficients. I have alpha, I have beta. Now I need to get gamma. And I'm avoiding complex algebra, aren't I, by this process? Oh, what did I say? Well, I said this partial fraction expansion is true for any value of s where it doesn't blow up. So you wouldn't want to plug in s equal minus 1. Then you get infinity equal infinity. That's not any good. That doesn't give you any information. You don't want to use minus 3 plus j4, minus 3 minus j4. That's not any good. But you avoid those singularities, and any other s, it's okay. Why don't we pick a convenient value for s? Minus 3. That would get rid of this guy, wouldn't it? And what else is it going to get rid of? The left-hand side. So that's going to help us a little bit. Let's now, in finding gamma, what we want to do is then pick a convenient value for s. And in this case, let's go ahead and let s equal minus 3. I'll do this if you didn't see what I was doing. Let me go ahead and just plug this in. Here's the left-hand side. There was the s plus 3. The denominator is well behaved, isn't it? It's a number. And so I end up with just 0 by evaluating that left-hand side. Then I have alpha over s plus 1, but s I said was minus 3. I have to keep that. Then I had this beta term, but that was now in the numerator s plus 3 over that denominator. I'm not going to write that down. I'm running out of patience and room. I now have minus 3 plus 3 plus the gamma times 4 over, now I will go ahead and write it down. I had the minus 3 plus 3 squared plus 4 squared. And that now gives me 0 on the left. I have alpha over minus 2. I had a 0 for beta. And I had a 4 gamma over 4 squared. I can clean that up if I multiply everything through by 16, and if I push the alpha on the other side, I now have 8 alpha is equal to 4 gamma. And I'm trying to find gamma. I already know alpha. Have to do the division right, but this now gives me 2 alpha. And alpha I already knew. And now I know what little q of t is. Q of t was the very first piece, which was this 2e to the minus t. Then I had a alpha e to the minus t, and alpha was 1/10. Then I had a minus 1/10, or beta, e to the minus 3t cosine of 4t, plus a 1/5, or a 0.2 e to the minus 3t sine of 4t, and all of that is for t greater than or equal to 0, and that's now my solution to my low-pass filter when that low-pass filter is hit with this exponentially damped cosine waveform. That's going to excite my system. I'm missing my trash can. Got moved. But we now shake that system, not with a pure sinusoid. It's now exponentially damped. But that excites what? That excites the initial or the natural mode in your system, which is e to the minus t. And your initial condition also excites that mode. So you have two pieces that are associated with the natural behavior of your circuit, and you have pieces that are associated with your forcing function. And that's your total solution or complete solution. Now let's say that I want you to sketch this using MATLAB. I want to see, what does Q of t look like? Maybe you can visualize that. Can you right now? What do you know about e to the minus 3t cosine and the same with sine? That's effectively just a cosine that might be shifted a little bit, or a sine that's shifted a little bit with an exponentially damped amount of e to the minus 3t. You can combine those because those frequencies are the same, the sine and the cosine. But let's just see if we can simulate this or plot this in MATLAB. Is it clear what I'm wanting to do? I now want to have MATLAB just give me a graph of Q of t. That's all I'm wanting. I've just found the solution. I don't want to have to sketch it by hand. I'm going to go to the computer and let MATLAB sketch it. There's two things that we need to worry about if we're going to plot this with MATLAB. One is, how long do we make MATLAB keep sketching? And I'll just say, how long should we simulate that Q of t expression? And the second question is, we don't want to miss anything. If something's bouncing up and down rapidly, or if it's decaying really quick, we want to capture that in our plot. We don't want to step over anything, meaning how fine should we chop up the time axis. And I'm going over this because on the final exam, a lot of times students miss this, and I keep thinking, oh, this is clear, it's obvious, and then I see the final exam and I go, oh, it wasn't so clear. So let's make sure this is clear. What do we have? We actually have, here is our expression. Q of t is now 2.1 e to the minus t. I've combined those first two. I had a 2 and a 1/10 plus an e to the minus 3t, and then I had a minus 1/10 cosine of 4t plus a 1/5 sine of 4t. And that could be a final exam question. People ask, are you going to give a MATLAB problem? Are you going to give a MATLAB question? Kind of. I mean, that's kind of what this is. I might say, give me how fast you need to sample, or how fine you need to chop up the time axis, and how long do you want to sample that, or what's the time interval of that sketch? Meaning, oh, I can sample at 0.1 microseconds, and I can simulate it for 2,000 years. Yes, you can. And you may get 1 point out of 100 on the final for that answer. So you want to give me at least some realistic values. We're going to try to capture this. You don't want to have the response invisible relative to the entire time horizon if you sampled or plotted this for 2,000 years in terms of t. So how do we pick some of these parameters? We want to find out how long, but let's first figure out how fine we need to sample. How quick do we need to sample? To give us some insight into that, we have this notion of time constants. And how many time constants do we have here? We have two damped exponentials, don't we? We have this e to the minus t piece. And if we said, well, the exponent, what I'm looking for is I'm looking for when that exponent looks like t over tau. So let me just say this minus t, I want to make that look like and minus t over tau. I'm just going to make this relationship happen. And now I need to find tau 1. The tau here is so benign that it makes it kind of confusing what I'm doing, maybe. But if we now solve this for tau sub 1, you get the first time constant, which is just 1. What about the next piece? Now we're wanting to make minus 3t look like something minus t over tau, and let me call that tau sub 2. The minus signs I can cancel, the t's I can cancel, I can solve for tau sub 2, and I end up with 1/3. I have those two things from the exponential decays, and I also have how fast this is shaking, don't I? Because one is, it may be really exponentially damped very quickly, or it may be shaking really, really fast, and one of those may dominate how much I need to sample, or how fine I need to chop up the time axis. What's my damped frequency of oscillation? 4 radians per second. So I not only have the time constants, but I also have the damped frequency. And I think I comment quite a bit, maybe too often, that you need to remember that omega is 2 pi f. So the damped frequency in hertz is 2 pi f sub d, but the hertz is related to the reciprocal of the period associated with that oscillating frequency, omega sub d. So I now have 2 pi over t sub d equaling omega sub d, which you just said was 4. And I can now solve this for the damped period of oscillation. And that's roughly 1.5 seconds. If I sort of approximate pi to be 3. It's a little bit more than 1.5. Are we okay with that? Now we know how long it's going to take to have one cycle of that damped oscillation happen. It's going to take a little bit more than 1.5 seconds for that to occur. And we also know how quickly the damping is going to happen. Let's just look at a damped exponential, meaning we have two things going on. We have in this example e to the minus 3t in one case times cosine of 4t. think we called this tau sub 2. That was 1/3, wasn't it? When is that going to effectively be gone? When will that squish everything? After 5 of those, right? After 5 tau sub d, this is now gone by 5 tau sub 2s. Or that's going to be gone after 1 2/3 seconds. And that's about the same time as my cycle of one oscillation being 1.5. If I sketch this, and again, you'll need to bear with me, but let's say there's 1/3, 2/3, 3/3, 4/3, 5/3. My damped exponential is going to start up here at 1. If this is now 1/3, it's effectively gone after 5 time constants. And my oscillating behavior and here you'll have to just humor me. This now looks roughly like that. If I just had an undamped cosine, it's going to have a period of a little bit more than 1.5, so I'm just rounding that around to be about 5/3. Meaning, what's going to happen? One cycle is not even hardly going to be finished before you can't see it at all, because we're going to take the product of this times that. Meaning, if I now did that, I would have this dashed envelope on both sides, and my result I told you I can't sketch. But that's what the exponentially damped, wow, I better quit while I'm ahead. That would be what the exponentially damped cosine would look like. Does everybody see that? In 5 time constants, which is almost the same as one cycle, we're done. But what else do we have? Or let's just concentrate for now on this piece. If I just had this piece, how fine would I need to chop things up? Well, let me give you some rules of thumb, and that's all these are. These people will go, well, where in the world did that 30 come from, or where did 10 come from? Well, it's actually just a rule of thumb. It's not a hard and fast relationship. We have the exponential decays, and there the rule of thumb is let's just maybe pick 10 points in one time constant. So we have 10 points per time constant. In our particular case, we had a time constant of 1/3. We divide that by 10. And that now says, oh, if you wanted to chop up your time axis based on that e to the minus 3t exponential, you would sample that or chop up that time axis with a resolution of 0.033333. And you'd probably just throw off the 3. You might even say, you know what, that's too messy. Let me just do 0.01. But now you know sort of the ballpark to be living in. You don't want to go the other way. You don't want to go, oh, it's 0.00 or it's 0.0333. Oh, it can be 0.06. You make it smaller as you approximate. Is that clear? Then we have the damped frequencies. And I believe the textbook says something like 30 to 60 points or samples per, let's say, let me call it a damped period. Meaning, in our particular example, we had a damped period T sub D, and we want to now, let's just do the smallest number of points. Let's say it's 30. What was T sub D before? That was pi over 2, wasn't it? So now we want to sample or put 30 points in that one interval. So this is now pi over 2 times 30, but pi we said was smaller than 3, or 3.14 is bigger than 3, so we can approximate that by saying, oh, let's make pi smaller. Typically, I don't like to make pi smaller, but this is the number pi, not the edible pi. So if there's a difference, okay? So we're okay with this numerical pi being smaller. We now have, this is 1 over 20, isn't it? And what does that end up being? 1/10 or 0.1 cut in half, so we have 0.05. And if we were just wanting to sample e to the minus 3t cosine of 4t, we would pick the smaller of the result that we just found. Meaning we have one piece of this process saying you need to sample at 0.05. The other piece is saying you need to sample at 0.033. So you sample at the finest one, 0.033, or even a little bit less. But the other thing that we have to remember is in this particular case, we had 2 exponential decays, didn't we? We had a time constant of 1 and a time constant of 1/3. We need to pick the smallest of those and then worry about the damped frequency. So now well, how do I want to do this? Let me, I guess, say what I just said before. If we wanted to do this in sort of 2 pieces, if we just wanted to look at each term and worry about each term separately, the one term, which is the more difficult term, involved this exponentially damped cosine. So we pick the smaller of, let me say this is now t sub sample sub 2. So we take the minimum of the time constant 1/3 divided by 10, or this damped period t sub d divided by 30, and what did we say that ended up being? We might just call that 0.03. Now if we go back and look, we also have this exponential decay of e to the minus t. Its time constant, tau sub 1, was 1. And if we based a sampling resolution on that tau sub 1, that would now be tau sub 1 divided by 10. We want to sample or put 10 points in every time constant. So over this entire interval of 5 tau, we're maybe putting 50 points. That's the idea. And maybe you want to put 100, so you would now divide by 20. Those are rules of thumb. Is that clear? In this case, we end up with 1 over 10, or 0.1. And now the ultimate sampling period, we have to compare all of these pieces. We may have 10 pieces to be looking at. In this case, we just really had 2. We now need to pick the smallest of all of these potential sampling periods. So the ultimate sampling period which let me call that T sub s, is now going to be the minimum of T sub s1 and T sub s2, which in this case, in this example, was T sub s2, which was the 0.03. Now we've figured out how fine to resolve the time axis. That's maybe why people didn't get it on the final. Took a while. But the idea is not that difficult. Basically, you're looking at all these poles in the S-plane and seeing how fine do we need to sample based on those poles. We now want to find out how long do we sample. Or how long do we run the simulation or the plot? So now we need 5 tau, don't we? But which tau? We have so many taus, don't we? Now we need to pick the tau that's the slowest, don't we, or the longest. So now we want to select the duration of our simulation, which I've got a lot of t's, don't I? Let me call that t sub n. You really have to worry about how these are subscripted. On the slowest or longest time constant. Meaning in this particular example, it's going to be 5 times the maximum of tau 1 or tau sub 2. Tau 1 was 1, tau sub 2 was 1/3. That's why we did our elementary school math, right? Which is bigger, 1/3 or 1? So now we know that it's 1. We can now say that this is 5 times the tau sub 1, which we want to run this simulation for 5 seconds. And by that point, the slowest, which is, sometimes we call it the dominant factor, that one will be finished dominating our total response. How can we throw a monkey wrench into this? Suppose now somebody says, wait a minute, I have a cosine or a sine and it's not damped. I have a sine or a cosine in this simulation and I want to see what's going on. How do I plot it in MATLAB? So if there's a sinusoidal, or if there, it doesn't have to be sinusoidal, if there's a steady state component, you might want to select or you might want to maybe say, you might want to simulate for 2 or 3 oscillatory cycles. And this is going to be based on after the 5 time constants or incorporating the 5 time constants. We're assuming now that the transients have ended. So if let's say that we had, instead of our x of t that we just looked at, let's say that x of t is now 4 cosine of 6t. What's omega sub d? That's 6, which is 2 pi f sub d, which is 2 pi over t sub d. T sub d is now 2 pi over 6, which is roughly 1, isn't it? It's a little bit bigger than 1 if you could do it many different ways. Let's just say it's 1 positive, a little bit more than 1. So if we looked at 3 oscillating cycles of that waveform, we would be saying, oh, Tn needs to be 3 times T sub d, which in this case is a little bit more than 1. So you may say, oh, that's 3 plus. Well, I'm just going to simulate for more than that. I'm just going to simulate for 4 seconds, something nice and clean. But this T end, as was just mentioned, that is actually assuming or assumes the transients have already died out. If we kept our original natural behavior in our low-pass filter, e to the minus t in there, we found that that was 5 seconds, wasn't it? So it's going to take 5 seconds to reach a steady state, and we might want to look a little bit beyond. Maybe we want to look 4 seconds beyond our transient. So we might want to simulate this for 9 or 10 seconds if we hit that low-pass filter with a cosine of a frequency omega sub d of 6. Questions on that? Let's quickly do the numerical solution. We've found now the true solution or the analytical solution. Can we actually approximate this numerically? Because maybe we want to do this quickly or we want to do it on the computer. Can we generate a numerical solution? And now we're wanting to solve this particular first order differential equation, where maybe to keep this consistent with what we had been doing, let's say that we haven't yet determined the A and the B, but we do know they're scalar. What am I going to do? Now I'm going to go to your middle school math. We've already done the elementary school math with the 1 is bigger than 1/3. Now we're going to do calculus. We're in middle school, right? We've advanced to calculus in middle school. What do we remember from our calculus relative to derivatives? That's roughly the change in Q over the change in time, isn't it? We just look at the limit as that delta t goes to 0 to give us the derivative. Well, the delta Q is just Q at t plus a little bit more time, capital T, minus Q of t. And if that's our time separation, delta t, that's the big T, little t plus big T minus little t. And that's now what we will use to approximate Q prime, where this denominator I hope it's clear, just becomes capital T. So that now we can say that we have this Q of T plus capital T minus Q of T all over big T that's the left-hand side. That's our approximation, and that's now A times Q of T, little t, plus B, X of T. Well, we want to run this simulation for all t, and we've now discretized little t, meaning we've now chopped t up into units that are capital T apart. Little t now we want to represent as little n capital T, meaning we're going to let little t be something like that. If we looked at what we have, if this is time, we've now broken this down. If this is nt, this point is n plus 1t, this point is n minus 1t, etc. And if this was q of t, which might be doing that, we've now said, oh, we're interested in that, and that point. Those are our q of nt's. If we replace little t with little n capital T, that approximation now says that we have q of little n cap T plus cap T minus q of little n cap T over cap T is approximately A q of nt plus B x of nt. And now I can clean this up by simply multiplying everything by capital T. So that now I have q of little n cap T plus T minus q of little n cap T is approximately AT q of nt plus BT x of nt. And let me put all of the earlier time expressions on the right, and I'm left with q of little n t plus cap t is approximately equal to 1 minus, what am I doing here? 1 plus at q of nt plus bt x of nt. Is that okay? And now if I plugged in what I knew for A equal to 1, B is equal to 1, and T, in our particular case, that was that 0.03, wasn't it? But maybe you go, you know what, I don't like 0.03. What do you, if you want to clean that up, what would you replace 0.03 with? Pardon? 0.01 maybe. Maybe that's cleaner for you. You definitely want to make it smaller, don't you? So this now might be there. And now you have a way to iteratively compute your solution. All you need to do is sample your x, and we were given x of t, and now you were given the initial condition on your voltage for your capacitor, and now you can simply iteratively generate the solution with this numerical approximation. Meaning we now, if we have t equaling to 0.01, we have Q of nt plus t equaling a sub d, let's say, Q of nt plus b sub d x of nt, where a sub d is now this 1 plus at, and b sub d is bt. Is it clear how you can numerically generate the answer? You could put this into a spreadsheet, and just each row could be a different time, and now we're getting time intervals of 10 milliseconds. We're now getting that capacitor voltage as it evolves every 0.01 seconds. And we know it started at 2. We know what x is. We can put in the appropriate x, and now we can just use this iterative relationship to simulate the solution to that low-pass filter. We'll pick up at that point on Tuesday.